All right, I'm seeing the numbers slow down a little bit, so I think I'll get us started. Hi everyone, and welcome to the second of 4 webinars presented by Integral Consulting's engineering practice. These webinars highlight some of the challenges that we face in our projects and some of the innovative approaches that we've used to solve them. Keep an eye out for future invites to some of these talks coming up. We're going to be talking about stormwater in early February, and then looking at changing PFAS regulations later on in February. So those are going to be really great talks as well. So keep an eye out for invites for those. My name is James Lesperance. I'm an engineer at Integral, and I'll be moderating today's discussion. A couple of housekeeping items before we get started. All attendees have been muted. If you have questions during the presentation, please ask them. And to do so, use the Q&A dialog box down at the bottom of your screen to type in a question. We'll have some time at the end to answer questions. We're hoping for a good discussion, so we'll get to as many of those as we can at the end of the talk. This webinar is being recorded, and you will receive an email after the talk with a link to the recording and to the slides. So check that out. Contact information for the speakers is on the next slide, but also in the webinar invite. So please reach out to them if you have any follow-up questions, or if you just want to tell them how great of a talk this was. So with that, I'll introduce today's speakers. They are Todd Martin and Susan Welt. Todd Martin is a registered professional engineer and hydrogeochemist. He has over 26 years of experience in the environmental field, specializing in environmental engineering, the fate and transport of chemicals in the environment, and remediation alternatives analyses. Susan Welt is also a registered professional engineer with more than 20 years of experience in environmental consulting and regulatory spaces. She's a recognized expert in the field of subsurface vapor intrusion, an experienced manager of soil, groundwater, and sediment investigation and remediation projects. And with that, I'll hand it over to Todd and Susan to start today's talk. Thanks.
Thanks, James. Thanks for that introduction. And I want to first start with saying a thank you to everybody that's attending this webinar. This is a topic that both Susan and I are quite passionate about. And we really are excited by the folks that are attending this and the interest that you're sharing. We know that you're very busy, and we really appreciate you taking the time out of your busy days to hear what we have to say. The topic, of course, is as the title suggests, is about conceptual site models. Now this isn't something that is new and exciting as are the topics that James talked about for our next upcoming presentations, emerging contaminants and PFAS, et cetera. But I think that the attendance that we have at this webinar really underscores the importance that CSMs actually play in the work that we do as environmental consultants or in the environmental field. The development and application of CSMs is really the centerpiece of how we navigate to a successful outcome in the projects that we work on. But unfortunately, what I've seen over the course of my career is that it's kind of a dying art. Too many people treat the CSM as a box checking exercise that they undertake too late in the process and then put aside too early before the project is complete. And what we hope to do with this webinar is really underscore the importance of not only developing a robust CSM early on in the process, but also continually testing and refining that CSM as the project goes and as we learn more through the process of understanding the site and applying that CSM to really help to ensure that we've optimized our chances of having a positive outcome. And we're going to use a couple case studies here to illustrate those points. So let's start with the basics. I've pulled out one of many definitions that you can find in a number of resources out there for what a conceptual site model is. But I really kind of like this one. This is one from the EPA. I've provided the EPA document number in case you're interested in learning more from that document. But basically, the definition they provided is the conceptual site model is an iterative living representation, emphasis added by myself, of a site that summarizes and helps project teams visualize and understand available information. So what does that mean? It's basically our attempt to explain ourselves. What do we see as going on as being important at the site based on the information that we have at hand, experience that we have from other sites, and experience that other stakeholders involved have conveyed. The act of putting together the CSM forces us to confront the things that we do know about the site, but also, just as importantly, what we don't know and the uncertainty that's therein. At the 30,000 foot level, CSMs all have common components. They discuss the sources of contamination, where contamination resides, what the processes are that could move contamination within the system and result in exposure to whether it's ecology or human receptors. Those are the common components. But one of the reasons I really like this definition here is that it underscores the need for the CSM to be a living representation, a dynamic document or piece. And that's really important because we are always learning at these environmental sites. No site is the same, and every site has complexities that we don't foresee, and we learn as we go. And you need to adapt as you learn that information. That's a critical piece that unfortunately is all too often ignored. So CSMs come in many forms. You've seen them in a variety of formats, et cetera. Most commonly, you'll see a CSM as part of a site investigation report or in a risk assessment document. And they vary in complexity and format depending on the project complexity itself and the needs of the project. They're often a combination of a text description of what the things that are going on, talking about those key components, sources, nature and extent, contaminant, fate and transport, et cetera. But also, I find that the graphics that can be developed are the most compelling pieces and the best ways to really illustrate what's going on. It's illustrated in the bottom diagram. And when a CSM is well done, it becomes the first point of reference in describing the site, whether that is to my staff when I have someone new who's coming onto the project. One of the very first things I do is provide them with the CSM and walk them through it so they understand what's going on and so that they have that context in executing their work and can do it well in a way that will help us get to our endpoint in an efficient manner. And in that manner, it serves as the touch point for all technical elements of the project so that the project can focus on what matters to move ahead in an efficient and effective manner. Susan's going to explain next why we care about that.
Thanks, Todd. Jess, do I have control?
Susan, you're on mute.
All right, can you hear me now? I have control.
Yep, you're good.
I think so. Thank you. So the fundamentals of the CSM and development and evolution of it is based off of the 5 questions we asked and learned about in school early on. Who, what, where, how, and when, right? We're really thinking about who are the stakeholders? How are they involved in the process? What are we trying to achieve? What's our goal? What's the regulatory environment in which we're working? What's the intent of the property now and in the future? What data do we need to understand? The site conditions. And what does the data indicate is happening now and over time? Notice I'm saying now and in the future, right? Thinking about that dynamic living representation that Todd said. We want to know where the site is. And we want to know why we care. This is the intent of the work to be done and the goal for which we establish for all the stakeholders. How are we going to get this done? How are we going to achieve this goal? and maybe more importantly, when, right? We all want to know when we're going to achieve something, whether it be the long-term goal, maybe site closure, or these milestones in between that we're trying to get to. These are the basic questions, but how we answer them will change based off the information that we have and the ever-changing environment in which we live, right? So we're going to talk about the case studies that Todd mentioned, and really with science and the development of where we are, things change. Our regulatory framework changes, things change, and we need to really be able to use that changing environment to modify our CSM. That's why throughout the entire project lifecycle, we need to reassess these questions. We need to go back and ground truth, a basis of our design, a basis of gathering information, the basis for making all decisions. Did that original work plan even make sense? And by asking these questions, we realign our current knowledge and our expectations with what's anticipated and what we now know so that we can make accurate and more timely changes and decisions to meet the stakeholder needs and objectives. Unfortunately, though, this process really falls short, as Todd says. Now, we really we start this in the beginning, desktop investigation, we're thinking about the CSM, we're getting some information, but we really take it forward to when we're collecting the data in the pre-design investigation or in remedy implementation, or dare I say even in OMM. So many times we're really focused on this initial check the box early in the process, and it becomes static. It's really never even thinking about transitioning into the other engineering stages or into that final OMM. And this can result in an incomplete or even incorrect understanding of the site conditions, design of a remedy, maybe it's inadequate, or even not even meeting the goals of the project. As more information is gleaned and stakeholder needs evolve, it's imperative that where the CSM is revised to ensure the most appropriate remedial approach will be implemented, designed and implemented, I should say. This entails remembering the CSM is dynamic. It needs to be continuously tested, refined, and updated throughout the course of the entire project, keeping in mind that the intent of the project-specific activity. So that's the long-term goal, and as I said, those interim measures that we're looking at, those milestones that we're trying to be at. The project team should challenge their preconceived notions and those of others, and be open to new information which will be used to test their understanding. We all know that this dialogue can actually get a better result. So we really need to think about how we redefine our framework on thinking about this. They said the following two case studies Tyler are going to talk about are dynamic in themselves in that one is based off of PFAS and one's on sediments, two complex types of projects that we work on. And what we found is by using the CSM framework, by really looking at the CSM, we're able to overcome potential conflicting approaches and develop an adaptively managed remedy. With that, I'm going to start with the first case study, and Todd will pick up when I'm done on this one. For this case study, though, I will say it is confidential, so I can't share a lot of the information about the site per se, but hopefully the issues that the project team has identified through this and encountered resonate with you all, because one is about PFAS, and I think many of us are actually focusing on PFAS or know about it, or it's coming apart in our sites, and we have to think about it, right? And the other is delineating. And what does that actually mean? As you see here, it's in quotes, because it's really hard sometimes to delineate when the environment in which you're working keeps on changing. So this site is in New York State, and it was a Department of Defense site. It's currently still a Department of Defense site, I should say. And it was found that aqueous firefighting foam, or some people may know it as AFFF, was used along a flight line. And the original investigations that were conducted in 2016, 2017, identified that PFAS were actually in soil and groundwater along the flight line. At this point, the agencies of the EPA and New York State got involved. They said, we actually need to evaluate this a little bit further and find out the nature and extent of what's happening from this PFAS that was used along the flight line. So the initial process, based off of this original data, was to actually think about getting some remedial investigations, some site investigations together to gather the information in this desktop investigation phase. We detected them, as I said, in the soil and the groundwater along the flight line. And that resulted in the agencies entering into an agreement with the Department of Defense. And on that agreement, it said we had 3 fundamental things to do, as you can see here: delineate nature and extent, assess baseline human health and ecological risk, and develop a comprehensive understanding of fate and transport of PFAS and groundwater flow. All really, really big concepts that we're thinking about here. And as shown here, we were thinking about doing it in a sequential process: desktop investigation, write a work plan, implement, get the information, evaluate risk, do your feasibility study design. However, as you can see here on the next slide, we had a big problem. The problem was we couldn't agree on what to compare the data to. Couldn't even agree on whether or not we should go out and collect data because we couldn't figure out the approach to do this. We couldn't agree on where to collect samples. We didn't even agree on what the receptors were going to be. So ultimately, after over 3 years of response to comments on work plans, we got a letter that basically said, if you don't do it this way, then we're going to go through enforcement. And at that point, we all sort of stopped and said, wait a minute, we agree that we need to evaluate what's going on at the site. We agree that PFAS could potentially cause a concern to human health and the environment. Therefore, let's go back to the fundamentals. Let's go back to the fundamentals of what a CSM is and say, as Todd and we've said now, it's dynamic, it's a living representation. And if the goal here is to move the project forward and get information, then we need to focus on how to even get that information, not the how, but what we're getting the information for. And getting the information for is what we need to think about. So after many conversations that we talked about, and we had a very large phone call to not just focus on the work plan, but focus on this fundamental of gathering the data, we realized that what we really care about is protecting human and ecological receptors. We're protecting the health of the environment and of people. And if that is our goal, irrespective of the 3 goals of that agreement, right? If the goal is ultimately to get data so that we can evaluate risk and address the potential risk, then we came up with a conceptual state model that was based off of this idea of risk. Now, as shown here, a lot of things are blacked out, as I said, but it's not the concept of what's in the CSMs that are shown here or parts of the CSMs. It's more the idea that we developed a conceptual state model for human health and ecological receptors. And what this did was said, what type of data do we need to collect? Where are the data points that we need to collect? Is it soil? Is it sediment? Is it groundwater? Is it potable water? Are there receptors we need to collect data from, like fish? Where do we go? On or off site? All these things we were looking at. We were looking at it from the basis of information to evaluate potential risk, not just delineating nature extent, not getting background or anything else. It was really, what are we trying to understand of where we're going? And from there, we collect the data for why those concentrations are there and what do we do about potential risk. So with this common ground, we actually could move forward. We have the path forward. We said, let's get some data. So we were able to finally get some work plans that were approved and go out in a phased approach of sampling. As I said, lots of different sampling has been done, and I think we're going on our 5th mobilization now. But at this point, we've been able to get the data, refine the information that we have, refine our CSM, say, okay, we should now focus our efforts in this area. We've identified there may be some background sources that we need to look at. Maybe there's other sources of PFAS in the environment, in the area. And what are we really thinking that we need to do? And based off the information that we've gotten in the data, we actually are letting that guide where we're collecting samples. And if a potential risk is identified by any of the stakeholders, again, as I mentioned, we have different criteria based off the different stakeholders are involved or regulatory agencies. So if any risk is potentially identified, the entity that has identified that potential risk is developing and implementing control measures to address the risk that they believe is there. And that could be a point of entry treatment system or fish advisories or any other measure that is potentially needed to address that potential risk. It's not focused on the PRP. It's not focusing on delimiting nature and extent. It's really all about protecting human health the environment, and ecological receptors. So again, the obstacle we've come across is don't worry about those three things, but really let's go get the information for that goal. So the lesson learned that we really focused on is that we shouldn't think about that process, that sequential process of get information, go to the next step, desktop investigation, site investigation, risk assessment, whatever it may be, not that process. Find the common ground, find the goal that you're working towards. In this case, protecting human health and the environment. If there is potential risk, address it. Don't wait for that process of doing a risk assessment and move forward. Think about interim remedial measures. And really rely on the dynamic nature of the CSM. Rely on the fact that we're going to get some information that will guide where we go next, where we sample, what type of sample, what should we focus on, what's our priority, where should the monies be spent. Really go through this process throughout and allow it to be a phased process. Don't think it has to be sequential. With that, this case study, as I said, is moving forward. We're still in the data collection stage, but Todd's going to provide a case study now where we've passed that. And actually, through the process of a dynamic CSM, they have achieved an adaptive remedial measure, and they really can manage the site adaptively. So Todd.
Okay. I think I've got myself unmuted. Okay, great. Thank you, Susan. Really appreciate that. And yes, I'm going to be presenting a case study on the Berries Creek study area Superfund site. And those of you who know me and know me talking about this site, you might be groaning because I tend to drone on and on about this site. So I'll try to keep myself focused. But this is an extremely interesting site that I'm very passionate about. And I'm going to highlight a few situations over the course of the project life where we use the CSM as a crucial tool for moving the site forward and really understanding what's going on. And as Susan pointed out, that led or helped to lead to the selection of an active management-based remedy that is really a positive outcome for everyone that's involved. So let me start with the fundamentals here. Let's give some background as to what I mean by the Berries Creek site. So Berries Creek is located in the Meadowlands of New Jersey, so very close to Manhattan. You can see Manhattan is over here to the east, and the Berries Creek site is defined by the watershed that drains into the tidal zone of Berries Creek proper. And Berries Creek is connected to the Hackensack River estuary. Tidal water flows in and out of the estuary daily, twice daily, so it's a significant component of what's happening physically and chemically and biologically within the system. And we're primarily interested in the tidal zone because that's where the majority of the contaminants reside, contamination that resulted from past industrial and commercial processes within the watershed drained into the system and then accumulated within the sediments. And now we have a legacy of contaminants both in the sediments in the water column and most importantly that has gotten into biota tissue. A real dominant feature of this system are the intertidal marshes that are present. There's over 700 acres of these marshes shown here in the photo to the left. Excuse me. Those are a dominant feature. They have significant influence on all aspects of the system, biologically, physically, and chemically, and will be a focus of some of what I discuss here later as we go into this. One point of reference for those of you who are football fans, the Meadowlands Stadium where the Giants and the Jets play football is located right here within the property boundary or the site boundary, so you can get a sense for where we're talking about. Right from the beginning, when we started the initiation of this project, we realized that this is a really complex site and that we needed to have a mantra of using the CSM as the cornerstone for executing this project. We started right away with gathering all the information we could and then recognized that there's a lot of uncertainty. We're going to learn a lot as we go. And we need to take an approach that allows us to refine our CSM and grow as our knowledge grows with the project. And in that way, the CSM became the vehicle by which we prioritized identification of data gaps and uncertainties, and how we could continually challenge our understanding to better understand the site. One of the things that we learned was really don't take anything as gospel. There were a lot of preconceived notions when we started this project based on experience that we had had at other projects or based on input from stakeholders. And we found that we needed to test everything because not everything was actually true or wasn't as important as it was at a different site. And so we knew that we had to use this wash, rinse, repeat kind of approach where we developed the CSM, we collected information to test the CSM, and then refined it again, and then repeated that process as necessary until we had the information and level of understanding that we needed to support understanding risks and identifying appropriate approaches for mitigating those risks. So we took a strategy of a phased investigation approach that tests hypotheses, reduced uncertainty over time, and moved towards that end goal. And that process really kind of established a mentality that ended up being reflected in the remedy that was selected, and that it is an adaptive remedy in which the remedy being implemented in phases, and we're going to learn information as we implement that first part of the remedy and determine what's needed for future steps after that remedy takes hold and its effect has been manifest. So, get to the next slide here. Start with a little graphic here showing an illustration of the BCSA system. You can see the marsh over on the right. This is a waterway in which water is moving into and out of the system, and the marshes flood during the higher tide periods and bringing in water and sediment into the marshes, et cetera. There's a lot that goes on at this site. Obviously, it's a very complex site with respect to the physical and biological processes, and one of the contaminants is mercury, and so we have a redox conditions are very important. Methylation, demethylation processes, et cetera, are all important considerations that we needed to factor into the CSM. For the sake of time, I'm going to keep this relatively focused and only touch on a few key points, which I'll talk about in a minute. But we use the CSM to identify initially a series of questions. We had a lot of information. There was information that was used to list this site on the MPL in the first place. There had been some research done by universities, Rutgers, et cetera, that we could use to develop an understanding. We relied on the expertise of the project team as well as input from other stakeholders to really get our initial understanding and identify key questions and concerns that we had and that others had regarding the system. And our focus was on looking at the sources of contamination and what was resulting in the exposure and uptake of contaminants in the tissues, in the biological tissues. We also wanted to understand the role of the marshes. We knew that they're a dominant feature, but there was uncertainty as to their role in terms of as a source or a sink for contaminants. What is their role with respect to methylmercury production, et cetera? As I pointed out earlier in the map, this system is connected to the Hackensack River, and water floods in and out of this system twice daily. It's the majority of flow that enters the system, and it's a dominant feature with respect to the hydrodynamic and sediment components, sediment transport components in the system. So we wanted to understand that better. The system is also influenced by major storm events. Over the course of our investigations, we had 2 hurricanes hit the site, Hurricane Irene and Sandy, and that had significant potential impacts to the system. And we needed to understand those impacts because they're going to continue to happen and likely are to increase in frequency and magnitude. And finally, what is the role of natural recovery in this system? Marshes are known to be net depositional in most cases, and we anticipated that would be the case in these systems. And under those conditions, we would expect natural recovery to be occurring, as well as in the waterways themselves. So we wanted to quantify that. So what did we know? More importantly, what didn't we know? I'm going to start with just some simple aspects of this CSM. And again, I'm not going to get into all the details. I'm going to focus on a few key hypotheses that we identified when we, after developing that initial CSM. And those are, one is the marshes are such a dominant feature in the system, and there you can see their evidence of their influence on the system just by walking around or floating around in a boat in the system. There is a ton of organic matter present, a lot of rafts of Phragmites debris or detritus floating around in the system that is also depositing into the waterway surfaces. The surface of the marsh has a significant detritus layer that's always present. And so we know that organic matter is continually being produced because of these marshes, and that likely has a significant role on all aspects of the CSM, and we needed to understand that better. Secondly, we anticipated that particulates were going to be a dominant feature with respect to contaminant fate and transport in this system. The primary contaminants are mercury, methylmercury, and PCBs, all three of which are known to strongly partition to particulates and most notably to particulate organic matter. So putting those two understanding together, we had hypothesized that organic matter, particulate organic matter, was going to play a significant role in contaminant fate and transport within this system. And then finally, there was a lot of concern early on about the role that the marshes may play with respect to being a source of contaminants to the waterways and to biota, specifically methylmercury. There's been quite a bit of research out there for other sites that have looked at mercury methylation in marshes and have found that marshes tend to be an area of elevated methylation rates as a result of the redox conditions associated with the flooding and dewatering resulting from the tidal processes, et cetera. And there was concern and is concern that methylmercury could be produced as a result of those processes that could be a primary source for biouptake of mercury into the food web. So we needed to understand that better. And so that understanding led us to do a series of phased investigations, as I described earlier, to really understand the site. We focused on understanding, the nature and extent of contamination as you would at any other site. We did surface water sampling, we did sediment sampling, we did high resolution cores where we sampled for contaminant and geochronological markers as a function of depth in the sediment column. And all of that was done to really pin down our CSM and the understanding that we had that the system is indeed, particulates do indeed play a significant role in contaminant distribution. We demonstrated that contaminants were associated with those solids and were predominantly in the sediment bed, and that natural recovery was occurring as a result of cleaner material coming in from the Hackensack estuary and from runoff into the system and depositing within the system. So we were able to show all of those things, but we were struggling with a couple things. One was the surface water quality was highly variable. We would see that concentrations of COCs varied significantly within a limited range of distance in the water column, and we also found that it varied between tidal cycles, et cetera, and we were struggling with really understanding what was causing that process. We also needed to understand better what the role of the marshes were. We knew that sediments were recovering in the marshes and that sediment was being imported into the marshes, but we didn't have a clear understanding of whether that meant that the marshes were indeed a sink for contamination or whether they may be a source. So this was all brought into our CSM, and those were the uncertainties that were identified, and largely based on discussions centered around this conceptual understanding. We took that information and went to literature to find a way to better understand those processes, because we knew that they would be important with respect to understanding risk and selecting a remedy. So we turned to literature, which is the standard thing that you would do in this kind of situation. And we looked to some work that was done by Dr. Brian Bergamaschi at the USGS. And what he had done was some initial work to use optically based instrumentation to correlate optical properties of a packet of water to the contaminant concentrations. He was looking at mercury and methyl mercury concentrations in that packet of water. So basically, you deploy this instrumentation, record measurements. At the same time, you collect a water sample and take it to a lab to get the concentrations. And you take those measurements that you've taken, correlate them to those water concentrations to predict the concentrations in the water column. And that gives you an advantage in that you can have those instruments out there for a long period of time, recording at a high frequency and get a high density of data that allows you to evaluate what's going on in the system. And so we took that research and really advanced the technique further to refine it, et cetera, and develop what we call the optics instrumentation package and technique. And you can learn more about that at the link that's shown here in the image, and we can certainly provide that to you later. But the key here is that the optics allowed us to really test our CSM and really understand some things that we were uncertain of based on the conventional techniques that we had used. And what we're able to show with this technique, and I'm not going to try to describe these graphics, but I'll explain what we were able to infer from this type of data, is that we were able to show that concentrations were changing in surface water as a function of the particulate behavior in the surface water. As tidal energy increased, i.e. Tides flooded in, the velocity started to increase to a peak, we saw concentration spike in the water column of particulate contaminants. And then during more quiescent periods, those concentrations would decline as a result of those particulates depositing back down to the water column. And this was all linked to a process that's in the literature, believe it or not, called fluff layer. It's been shown that there is a layer of material that forms in these types of systems of unconsolidated, relatively lower density particulates that can form at that surface of the water column, or sorry, of the sediment bed, and then be resuspended when energies are increased during tidal flooding or during storm events and those kinds of things. And we're able to show with the data that we collected that the data is consistent with these fluff layer processes that we had hypothesized were going on. And so we were confident that the waterway sediment was the source of contamination that we were seeing in the water column. And the reason it was so variable in our surface water samples is because tides were constantly going in and out, or different tidal conditions at any given time, or a storm event may have happened and moved materials to different parts of the system, et cetera. But we could readily explain it by having this optical instrumentation that we put out there for a month, for example, and collect data every half hour or every 15 minutes and really link those concentrations and their changes to what was happening, the forcing that was happening within the system. We also took that technique and combined it with some flow measurements to look at the other question that we had. What is the exchange between the waterways and the marshes? So by adding flow measurements at the same time that we were taking these concentration measurements, we could take flow times concentration to get mass flux, which is really the holy grail for anybody who's an environmental scientist. And we were able to show that the mass flux was from the waterways to the marshes for particulate contaminants, PCBs, particulate mercury and methyl mercury were all moving from the waterways into the marshes. We could show that very conclusively in every case that we looked at it. We also showed that dissolve phase mercury and methyl mercury was actually predominantly coming from the marshes to the waterways, which is consistent with what was had been speculated based on research at other sites. However, because we were able to do mass flux calculations, we could show that migration of dissolve phase mercury and methyl mercury was very small relative to the flux of particulate mercury and methyl mercury into the system. So in other words, there was a net import of mercury and methyl mercury and PCBs from the waterways to the marshes. And that was critical to design of the remedy that was selected. So we took that information and were able to really refine our CSM and show with confidence, with data, that these are the processes that were occurring. This illustrates that fluff layer process where particulates are being resuspended from the surface of the waterway sediment into the water column, and then during quiescent periods, they would deposit back down. There would be interaction of COCs from the waterway sediment bed to those particulates, and that was a process by which we were seeing contaminants get into the water column. And in turn, during tidal flooding in the marshes, those COCs would be carried into the marshes, and some of them would deposit there and accumulate over time. So this was really important because now we were able to demonstrate that the waterway sediments were the source of COCs to the water column and in turn to the marshes. And that was a framework by which we could design our remedy. So with this information and this very robust CSM that we were able to develop, the EPA had the confidence to select a remedy that was an adaptive-based remedy. And that means that the remedy focuses initially on source control in the waterways. The remedy will involve a removal action in the upper parts of the system of waterway sediment, and then replacing that with clean backfill, such that we have reduced the exposure to those contaminants that were present in those waterway sediments, which were elevated, and also reduce the potential for contaminants to be transported from waterway sediment to the water column and in turn to the marshes areas downstream. And so based on that, EPA selected this adaptive remedy that has this first phase of removal action, source control, and then monitoring what the response of the system to that, knowing that by eliminating or reducing that source of contamination to the water column, we're enhancing the natural recovery of the system in the marshes and other parts of the system. And so we want to see how the system responds to that, how effective the source control is at enhancing natural recovery, so that in the next phase, we anticipate that we'll be able to rely on natural recovery for a good portion of the system, if not all of it, down the road. So that was obviously a very positive outcome in that it met stakeholder objectives of minimizing the disturbance of the marshes, which are considered a valuable ecological resource, as well as a resource for reducing storm energies during these hurricanes, et cetera. That it also reduced the costs. You know, when we first started this project, there were some that wanted to see the marshes completely removed from this system. This is 700 acres of marshes. Not only would that be very costly in terms of a remedy for our client group, it would also be a very poor remedy with respect to sustainability metrics. And so we were quite pleased with the outcome and the selected remedy, and we're moving forward at this point on the design process. We're currently at the 95% level of design, and the conceptual site model has continued to be a very important piece in terms of informing the design and moving forward with plans to monitor for performance monitoring. For example, the conceptual site model was the basis for a component of the design to place the backfill in a series of 2 lifts. We recognize that particulates are such an important component of this process, and that the active dredging has the potential to result in particulate residuals that could be result in recontamination of remediated areas, as well as contamination distribution into the marshes, et cetera. So the backfill will be placed in a series of lifts to first minimize the influence of residuals, and then once that has settled down, place a clean layer at the surface that will have enhance our effect in terms of reducing the exposure concentrations and reducing migration of COCs. Further, the CSM is continuing to be used as the basis for developing the performance monitoring program for the system. We've developed a plan that is centers on this understanding that I've described. We're monitoring the response of particulates in the water column. We're monitoring the distribution of particulates as they deposit in the system post-remedy in the marshes and in areas downstream, and an effort to really understand the influence that the remedy has had on what we've identified as being the most important process within this system. And so that monitoring program is pretty unique in that it's not really designed to just say, hey, sample after you're done and show that you've met concentration goals. Rather, we're monitoring to show that the remedy has had the impact that we've expected. And then at that point, we will do another risk assessment, determine what the residual risks are present, and then use that information and the understanding of how natural recovery is occurring to make the next decisions in terms of the next phase of remedy. And with that, I'm going to pass this back to Susan. Thank you.
Thanks, Todd. What I really want to focus on here is the fact that the dynamic nature of the sediment project, Berries Creek, that Todd talked about really falls well within the dynamic nature of the conceptual site model. And what we need to focus on here is that everything we are talking about is intentional. We are intentionally looking at data. We are intentionally looking at the ability to move a project forward. We're intentionally looking at what the data means and what are we trying to achieve? What's that project end goal? So really looking at the CSM, we are able to guide the project. We're able to ask the questions intentionally, looking at the data, thinking about what we want to achieve at each step. We want to have it be that iterative living representation of a site that summarizes our understanding, visualizing it, as Todd said, really seeing what it is. It's easy to see a picture and say, this is what we're looking at, as opposed to just the words or data or something else, but really having it be that you can understand it very quickly at a snapshot, but yet there's so much complexity within it. Understanding that information, that data, and identifying the investigative data gaps, or thinking about those innovative approaches to get more data, thinking about those optics or something else. What is it that's going to help us get the information we need to truly understand the site conditions, to understand what else we may need, and what's going to guide development of the appropriate remedy, guide appropriate OMM, guide appropriate whatever it may be, so we can achieve our stakeholder goals. And it really makes us think about the data that's being generated. And we have to ask ourselves, is this what we expected? You know, Todd said that the data we obtained actually in the optics supports what's in the literature, what's really happening, right? But it makes us think about it and really ground truths where we're going. It makes us think, does this make sense, right? Really reassessing and questioning ourselves. And asking these questions each time enables us to revise the CSM at each step of the project, right? It's really go back. Is there more risk? Should we think about something else? Is there a different OMM strategy? Does this make sense? By going back, we can go through the entire approach and really think about, do we need to make a change? Should we change it now? And by doing this in the iterative process, having the dynamic nature of this living document, we actually can represent our understanding and propose changes to stakeholders and regulators in a timely fashion. And by doing that, we can actually try to reduce costs and liabilities because we're addressing it in a more timely, innovative fashion. With that, I'm going to pass it off to James, who can see if there's any questions. So I thank you all for listening.
Yeah, thanks, Susan. Thanks, Todd. With that, we do have a couple minutes here for questions. So yeah, use the Q&A dialog box down at the bottom of the screen and feel free to type some questions in. And while I'm giving folks a few minutes to do that, Susan, I have a question for you. With your PFAS case study, I think you're hitting on a challenge that a lot of us deal with when doing investigations or using CSMs, and that's that regulators they feel like they only have one chance to gather all the data on a site, or clients or other stakeholders may not want to, go back to the well, so to speak, and continually collect data. Given your experience on this site, what advice do you have on getting stakeholders on board with a dynamic investigative approach?
Thanks, James. That is a critical question that we all have to face sometimes. And I think that the biggest milestone we achieved at this project was having some real conversations Originally, it was all, we write a work plan. We thought we would just move through the process because we got an order and it said this is what we're supposed to do. And, we go, the consultant is hired and we write a work plan and say, this is what we do. We submit it. And then it's like, wait a minute, that's not what anyone wanted. And really the back and forth, the comments and response to comments made it a very confrontational situation, and that no one was really listening anymore. They were lost in the first few words of a 200-page document, right? And so really the advice I'd give is having that conversation, that open dialogue from the beginning, and really understanding what our approach is going to be. Collect some data, understand, go back, and focusing on that common ground. What's the intent, right? The big picture, not those mini milestones of getting the process forward, but really the intent of what we're trying to do.
Yeah, completely makes sense. Thanks. I have a question here. Maybe this is better for Todd, but either of you can answer this. Do you have any insights on using geostatistical techniques to help with your risk assessments and CSMs? I'm aware that it will be a product of data spacing. So insights on using geostatistical techniques to support risk assessment or conceptual site models.
Well, I can add my 2 cents. I will say it's not my area of expertise, but what I will say is that I'm a fan of using any technique that helps you understand the site better. And geostatistical techniques are just one of any number of techniques that I would say are in the toolbox to do just that. We have used them on a number of projects to really support our understanding better and illustrate that understanding better. In addition, I think that those types of techniques can be used to help reduce uncertainty and in a way understand uncertainty better in terms of what you know about a project, the distribution of contamination or other aspects of the site that are important to know, their spatial distribution, et cetera. Susan, do you have anything to add to that?
No, I think, as you said, there are many tools in a toolbox, and I think they should all be considered when doing the evaluation at any step, right? So you may have one tool you're using in the beginning, but as you refine the CSM, another one comes up. And so it's really the idea of what's the appropriate tool at that time to answer that question. And so I wouldn't rely on one specifically. I think we really need to think about the dynamic nature of even the tools that we have for answering the question that's there at that time.
Certainly. Yeah, and I think, Todd, that the optics work at Berries Creek is a good example of maybe a non-traditional tool that was able to provide a higher density of information than the kind of the complementary, quote unquote traditional method might have provided. Yeah, and on that nature, I think, Susan, of what you're saying about using the appropriate tool at the appropriate time. Todd, maybe to pick on you a little bit, the Berries Creek CSM case study is a great example of how the success of a dynamic CSM. Do you have, or have you run across in the course of your career, any examples of where a lack of adherence to the dynamic CSM approach has led to maybe less than optimal conclusions or less than optimal movement of a site?
That's a good question. I could probably point to several examples, but one immediately jumps to mind. Unfortunately, I can't give you the details. It's a confidential site, but I can tell you a little bit about the issues that arose. At the site, there's been over a decade of investigations that have been done, and it was part of a process where the two parties were working to try to achieve a consensus on what needed to happen. This is again another sediment site, and there was a lot of excellent work that was done to characterize the site. However, as a third party, kind of reviewing all the history of the project and looking at the work plans and the documents that were produced, it was clear there was no clear adherence or kind of using the CSM as a checkpoint. In fact, the CSM was not really clearly articulated at any time. And so And what that led to, although the work was really good technically, it was somewhat unfocused. And I, in my opinion, that's of course my opinion, in reviewing this, felt that there was a lot of work that really didn't get to really understanding the site. And perhaps even more importantly, by not using the CSM framework, I found that there was a lot of, or there tended to be kind of this, hey, we think this is going on, but they never tested it and they never confirmed it. And for somebody who comes in as a third party and looks at it, I see a great deal of uncertainty in some of the conclusions that were reached. And unfortunately, that uncertainty it contributes to uncertainty in terms of the effectiveness of what the selected remedy is and whether it can actually be implemented in a manner that will be effective in achieving the project goals. So again, I can't give you the specifics of this, but I can tell you that it led to some significant challenges as we move forward on this project.
Yeah, that completely makes sense. So you can do all the fancy analysis and modeling and anything else up front that you can get access to, but unless you're field testing and testing the conclusions, then maybe has limited value. All right, I think we have time for one more quick question. Go ahead, Susan.
I just wanted to reiterate here one thing, in that the CSM is a communication tool. And so if there's questions raised from the CSM, then we haven't communicated clearly enough. And so really focusing on the fact that we should be able to have a clear understanding from the CSM is the goal. So, sorry.
No, definitely. Well, I think we're just about at the top of the hour, and I don't want to keep people past our time. So really appreciate everyone calling in and listening. Thank you, Todd. Thank you, Susan, for a great talk. And like I said at the beginning of the hour, keep an eye out for invitations to Integral Engineering's future webinar talks. We have a great one coming up looking at emerging contaminants in stormwater, and then following that, we'll have a great discussion looking at the changing regulatory landscape with respect to PFAS. So thanks again for calling in. Thank you, Todd and Susan, and hopefully we'll be talking to you soon. Thanks a lot.